From Department of Biomedical Engineering, SNS College of Technology, Coimbatore. And in this December month lecture series, we are going to discuss about the transient analysis of neuromuscular reflex action under physiological control systems. And here in neuromuscular reflex motion, examination of dynamics of neuromuscular reflex motion can yield valuable insight into the status of patients who have neurological disorders. The patient is seated comfortably and his shoulder and elbow are held by adjustable supports so that the upper arm remains in a fixed horizontal position throughout the test. The subject's forearm is allowed to move only in the vertical plane. At the start of experiment, he is made to flex his arm by pulling on a card that has been attached to a cuff on his wrist. The card runs around a pulley system and supports a sizable weight. Here, then at time t equal to 0, an electromagnetic catch is switched off so that an additional weight is abruptly added to the original load. Changes in angular motion theta of t of forearm about the elbow are recorded during and after the quick release of the weight. Here the limb dynamics is represented as m of t and mx of t. Here the angle is theta, mx of t minus m of t, which is equal to j theta. C. While coming into muscle model, although the reflex involves both the biceps and tricep muscles, we will assume for simplicity that the net muscular target in response to M is generated by a single equivalent muscle model. See the single equivalent muscle model here. The target net muscular torque in response to M is MO of T. Here we have B elements for muscle model. Theta and theta 1, the output is m of t. Here m of t is equal to k of theta minus theta 1. Here m of t, which is equal to m 0 of t plus b theta 1. Here see the plant equation. Although this reflex involves both the biceps and tricep muscles, we will assume for simplicity that the net muscular torque is response to M is generated by a single equivalent muscle model. So the equation becomes bj by k theta plus j theta plus b theta. Here the dots in theta, it represents the differential equation orders, which is equal to mx of t minus mo of t. O is your output of muscle system. Initially we have 0 as well as we have finite states. Here mx of t minus mo of t. See here in muscle spindle model, here this model describes the dynamics by which changes in theta are transduced at the level of muscle spindles into afferent neural signal. They later travel to the spinal cord, which sends out afferent signals to the contractile machinery of the muscle to generate MO of T. Here MO of T, which is equal to beta theta minus theta 2. Here C, here we have KSP, BS and tau naught, KSS, theta and theta 2. Finally, we have MS for muscle spindle model. Here MO of T, which is equal to beta of theta minus theta 2. Here, what is this KSS, KSP? What is tau naught, tau 0 or tau out? Here, the dynamics of muscle spindle model may be characterized by the following equations. MS equal to KSS of theta minus theta 2 and MS equal to BS theta 2 plus KSP theta 2. And another important factor that must be taken into account is that although theta is sensed virtually instantaneously by the spindle organs, there is a finite delay before this feedback information is finally converted into corrective action at the level of the muscle. This total delay TD, it includes all lags involved in neural transmission along the afferent and efferent pathways as well as the delay taken for muscle potentials to be converted into muscular force. So finally, muscle spindle model output MS is equal to KSS theta minus theta 2, which includes the total delay TD. Here MS equal to BS theta 2 plus KSP theta 2. MS equal to BS theta 2 plus KSP theta 2. C. Muscle spindle model is shown here. Here the input is mx of s, which is fed into 1 by bj by k multiplied with a square plus js plus b, and the output is s theta of s, which is fed into 1 by s. The output is theta of s, and here we have e power minus tau. Here we have here the term which indicates the delay, and we next term also delay, tau s plus 1 by eta by tau s plus 1, and finally we have beta, muscle spindle model element, and we have mo of s. Here we have summing point plus minus, and by eliminating the intermediate variables ms and theta 2, the value becomes mo plus mo by tau, which is equal to beta of theta of t minus td plus theta of t minus td by eta tau, where tau equal to bs by kss plus ksp and eta equal to kss plus ksp by ksp. Here we can determine the neuromuscular reflex motion with the help of these elements. Thank you.